here's what I'm going to do today. First, I'm going to give you the motivation for the problems that we're going to study, and I'll tell you what the problems are. And then I'll get into computing symmetries. This is going.
There's a sound.
I'm speaking. No, I'm kidding.
You don't hear it?
Yeah, I hear you. Ventilation.
Something about the sound?
Okay.
No? Okay.
Sorry. Okay.
And then I'm going to talk about computing symmetries, which is going to be a major portion of this talk. It's about if I hand you a certain subvariety or a subset or something of a vector space, what are all the linear transformations that preserve it? Okay. After that, we're going to go back to null cones and Hilbert-Mumford criterion that I'm going to recall from last time, and then we're going to do a conclusion, which is the main result. And finally, I'm going to talk about computing vanishing ideals if I have time, which I probably won't have time. Okay. So I'm going to start with the motivation, and only then I will define the problems for you. Okay. So the motivation starts with these problems of polynomial identity testing and non-commutative rational identity testing. And the stories, the way I've presented them, they're going to go sort of parallel. So this polynomial identity testing is the word problem for the function field. This rational identity testing is the word problem for the free skew field, which, if you remember from last time, which you don't have to, I denoted in a funny way. But in terms of concrete language, what is a polynomial identity testing problem? It asks you, given a polynomial expression and another polynomial expression, are they equal or not? Right? And the problem, the question is asking for some sort of algorithm for this, hopefully efficient. Okay. And on this side, you have expressions that are slightly more complicated, in the sense that you're in the non-commutative setting, so it matters whether you multiply on the left or the right. And I also allow you inverses. And the problem with inverses is you can have nested inverses, which you have no way to clear denominators. Yeah. And so you have all these issues, and I put up an expression that I'd never put up before. Probably nobody else has ever put it up before. So you might ask yourself whether these two expressions are the same or not. Maybe Avi already has a guess.
Yeah, they are.
Where did I get it from?
From right in our paper.
Yeah, no, did he really?
Yeah.
Okay. Well, I didn't get it from his paper. I worked it out.
Yeah.
Okay.
You could have put the same expression on the left also, because
Yeah,
you
exactly.
don't have to have polynomials, the rational functions in the commutative setting are
Okay.
also interesting, but happen to be equivalent to the polynomial expression.
Excellent. Okay. With that comment, so let me.
Sorry, I'm confused about the use of the word problem.
Are we going to go down this road again?
This is how they call isomorphism in many settings.
So it's not. It doesn't have to be a group. Which is
No, it doesn't have to be a
Group.
group. Yeah, word problems, you have some algebraic structure, and different elements have more than one representation. And you want to know whether two representations are of the same element. This is called the word problem.
So you're just using it to confuse us.
Well, somebody gets confused when I don't put it, and somebody gets confused when I put it. And so, anyway, if you know polynomial identity testing, you don't have to listen to this. Anyway, so. Thank you. So polynomial identity testing is in BPP. This is, if you want to think of it, it's a randomized polynomial time algorithm with very little error. And the way to do that is, if I give you two such expressions, you plug in some random numbers for A and B, and with high probability you will be able to decide whether it's equal or not. Okay. And perhaps a big important problem in complexity is to try and find an actual deterministic polynomial time algorithm. And if you did, it implies some consequences that are very close to P not equal to NP. If you know what they are, you know what they are. Otherwise, you just think of this as something close to P not equal to NP. Okay. And on this side, this is the non-commutative setting. It's not quite so easy to plug in something in here, because you can't plug in numbers. It's a non-commutative thing and you want to test it. It doesn't make sense to plug in numbers. But there's a lot of work that goes into it, and eventually we come out with a polynomial time algorithm, and it's non-trivial. So just to point out, even decidability is non-trivial, requires a non-trivial argument. But here's what I want to say. I won't tell you about the algorithm. That's work that's been done long enough ago that I'm bored of it.
Is it easier to plug in matrices randomly than to do this lot of work?
Yes, it's easier to plug in matrices, but of what size? And that's really the question. Yeah. If you could tell me what size matrices I should plug in before I give up, that would give me my randomized algorithm.
You have a non-random P.
Right. Yeah.
Okay.
And then you take that and
Even a randomized algorithm
then-
is non-trivial.
Okay.
We have to know what. Yeah.
Okay, so this problem of polynomial identity testing, you can reformulate it as symbolic determinant identity testing, which I'm also going to just call commutative rank, which is going to be membership in a certain subvariety. Okay, and that subvariety, I've written it out for you. It's m tuples of n by n matrices such that the formal linear combination is singular when considered as a matrix with entries in this function field. Okay, and this is the same thing as saying the determinant is 0. Identically 0. Okay, which is what you might think symbolic determinant identity testing stands for. Yeah? Okay. And on this setup, on this side, it's the same thing. You take this rational identity testing and you can write it as this problem of computing non-commutative rank, which is membership in a different subvariety, but looks very, very similar. And here it's m tuples of matrices such that the formal linear combination is singular over this free skew field. Okay. Yeah? So far both stories look pretty much the same. Now, this algorithm that I didn't tell you about uses basically this particular feature, that this particular variety is the null cone for a particular action. And this action is called the left-right action, where the group is a product of SLN and an SLN, and the vector space is of course m tuples of n by n matrices. And the way it acts is one of the SLNs acts by left multiplication and the other one acts by right multiplication with transpose for each of the matrices. Okay. Now, what I want to stress is that this feature is crucial in giving this polynomial time algorithm. Okay. So now the natural question is, you want to find a polynomial time algorithm for membership in this guy. Wouldn't it be nice if it were the null cone for some group action? Okay. There are other reasons to hope for null cone of some group action, because if you just have a group acting on a vector space, there's these analytic algorithms that you have, which say which sort of use gradient descent to give you a null cone membership algorithm. I don't want to get into these algorithms, but maybe if you get a good enough group here, you get a polynomial time algorithm. Okay. So let me just remind you very quickly what the null cone is. A group acting on a vector space, the orbit of a certain point is all the points that it can go to by applying group elements. And the null cone is a set of all vectors such that the origin is contained in the orbit closure. Okay. So now what I'm going to do is I'm going to abstract out the problem a little bit, where I lose my focus on what exactly this variety is and try to ask these questions in more generality, just to get a sense of what you can do for this problem. Okay? So if you strip away the context and everything, what am I really asking? I'm giving you some subset of a vector space, and I'm asking you, is this the null cone for some group action? Yeah? That's the important problem here. Somebody hands you a subset. Does there exist some group with an action such that the null cone is their subset? Okay? And I'm going to maybe ask for reductive, but don't think about it too hard now. Yeah?
Is there some reason beyond the fact that there's a theorem in the non-commutative case that characterizes this singular set to expect the singular set in the commutative case to be a null cone? I mean, is it just wishful thinking, or is it?
It is wishful thinking.
Analogy should be. I mean,
Well, because I know the answer to this question, I have to say it's wishful thinking. Well, it's sort of both stories kind of run parallelly. And the reason you might want to answer this question is it might tell you why this problem is harder than that problem. Or not.
I mean, people have been trying to solve this de-randomization problem for 40 or 50 years. This, the PIT problem. It's a trivial probablistical problem. And we have no idea why we cannot do it. It seems like maybe one of the easiest problems in DCP. The trivial probablistical algorithm works, and we cannot, despite having many tools developed over the years, we cannot find the randomization. So one explanation is this fact that the deterministic algorithm will lead to lower bounds, which are hard to find. So that's the discovery of Cabanas of Pagliazzo. But these recent algorithms, these analytic algorithms that work whenever what you have is a null cone, suggest, oh, maybe this will work, or if it doesn't, why doesn't it? So this was basically the reason we asked ourselves this question. It's not, I don't know that anybody else asked this question or this kind of question, like you pointed out last time.
Right. Well, until you come up with this story, nobody has a reason to ask this question.
Well, there is a reason. I mean, algebraic geometers ask questions about their varieties, whether they have certain properties. Are they Cohen-Macaulay, for example? Various other structures that make varieties more special. They care about smoothness. They care about all sorts of This particular one, we don't know that was asked before, but that's the reason.
Okay, so getting back to the problem.
But let me just say, I mean, it's a very natural problem to ask whether your variety has symmetries and what are they. It seems extremely natural. I am surprised that well, it was almost not asked.
Okay, so coming back to the problem, whatever the motivation is, you have a certain subset of a vector space, and you're trying to ask if there is a group such that the null cone is the given subset that you have. Right? It's sort of an inverse problem. Usually you might expect somebody gives you a group acting and then asks you to tell me what the null cone is. So this is kind of an inverse problem where you're given what the null cone should be and you have to recover the group. Okay?
Like, do you want to recover the group, or do you just want to see is there a group?
Well, if there is a group, then I definitely want to recover it. Yeah? Okay. If there isn't a group, then I can't recover it. And so the first observation that I want to make is whatever this null cone is, whatever this group is, it would have to preserve this null cone. Yeah? All I mean is if you have a vector whose orbit closure contains the origin and you move it around by some element of the group, then it's the same orbit closure, right? So moving along, if you act by the group on the null cone, it's going to keep the null cone back to itself. Yeah? So in particular, whatever this group is, it has to stabilize this set if it has any chance of being the null cone. Okay? So I'm going to ask the second question. Given some subset of my vector space, what are all the linear transformations that preserve this subset? This is an even more natural question to ask, and probably even more natural to ask in far more context than the one I've presented. Okay? And basically why this is important for us is that, look, initially you were searching for all kinds of reductive groups acting. If you can compute this group of symmetries, then you can restrict your search to subgroups of this group of symmetries. okay, which is hopefully much smaller. Okay, baby steps. Okay, what did I want to say next? Okay, so now I want to ask this question. Somebody gives you a subset in whatever fashion that you might expect, and they ask you what are the linear transformations that preserve this exact subset. This is a hard problem to try and compute explicitly. Yeah, you have this particular subset. What are all the linear transformations on this vector space, which is Mn squared dimensional, that preserve this particular subset? Okay, that's a hard computation. It's not even linear computation. I hope you realize it's not a linear computation, because whatever the outcome is cannot be a linear subspace. It's a group. It's cut out by polynomials in some various degrees. It's not going to be easy to describe this if you try to just compute it on the nose. So here's the first step that I'm going to do, is I'm going to try and convert this into a linear algebraic problem. Okay, that's the first idea. Okay, if you can't see this board, come in a little bit. So subsets are not linear, but subspaces are linear. Right? So if I asked you, instead of all the linear transformations preserving a subset, if I asked you all the linear transformations preserving a particular subspace, that's much easier to compute. Yeah, that's much easier to compute. It's just some block triangular matrices. So what am I going to do? I'm going to replace this subset with a particular vector space or a subspace that captures everything you want to know about this subset. Okay? The only problem is, this subspace is not going to live inside my original vector space. It's going to live somewhere else. Where is it going to live? It's going to live inside the space of polynomial functions. Okay? So all I'm going to do is I'm going to consider all the polynomial functions which take the value 0 at every point in the subset. Okay? And this is one of the basic one of the basic reasons why algebraic geometry works really well is that these two guys contain exactly the same information. So whatever you want to understand about this, you should be able to understand using this. Okay? So what I'm going to tell you now is the group of symmetries is going to be all those linear transformations in GLV that preserve the subset, which is the same thing as all the linear transformations that preserve this ideal. Yeah? Okay? Now I'm going to point out one more issue here. If you think of this polynomial functions or you think of this ideal, okay, this is a linear subspace of that, but both are infinite dimensional spaces, right? This is again a problem for computation. If you wanted to compute this, how would you do this for infinite dimensional spaces? Okay. So I have two remedies for this, and I'm going to tell you both, but I'll of course use only one. And the first remedy is, suppose your ideal was generated in degree at most d, then you just restrict yourself to the ideal to degree at most d. Okay, generators of the ideal capture all the information you need to know about the ideal, so there's no loss of information. Okay. And the other one that's slightly more complicated, but you still have to believe me, is suppose I look at a particular degree, degree e. So I have this ideal, I look at the degree e, polynomials that vanish on my subset, and if the 0 locus of that is precisely my subset S and nothing more, then I claim that you can just understand the linear transformations that preserve this particular degree. Okay? So you don't have to, I'm not going to tell you the proofs of these are not that hard, you just start writing them down and they work themselves out. But what I want to point out is basically this. I took a highly nonlinear problem, right, and I made it slightly more linear. I made it slightly more linear in the sense that I took out this subset and I put in some subspace of a finite dimensional space. Okay? But again, the problem still remains that whatever the answer for this is going to be, it's not a linear subspace, right? It's going to be some subgroup. How would you compute this subgroup? So I still need one more level of linearity. If I really want to make computations, and this is probably a general philosophy that everybody knows to some extent intimately in the heads at least, that if you really want to do a computation, it has to be linear algebra. Right? The more complicated the computation, the happier you are if it's linear algebra. Okay, so I'm going to pause for a minute. Yeah.
The last question you written there, is that always true, like for any given idea there is a single degree where you can find the neighbors for that idea?
Okay, so the one thing that I didn't really specify is that this is a cone in the sense that if you scale it up, it's invariant under scaling. Therefore, the ideal is homogeneous. Once you have it's a homogeneous ideal, you take all the degrees in which the generators are, take the LCM for example, and you'll be fine. Yeah, so it will exist. But of course, if this degree becomes really large, then again it's a problem for you. Okay, so just remember the overall picture. We have this highly nonlinear computation. I made one part of it linear. Now I'm going to try and make the other part of it linear. Okay? And to do this, I have to teach you Lie algebras. Okay? Which is what I'm going to do now. Okay. So I hope everyone's seen a group before. Okay? Now, whatever version of group you've seen before, I'm going to put it in a different, maybe you've seen this particular version before, but I'm going to say it in a particular fashion. A group is a set with a multiplication map from G cross G to G that tells me how to multiply two elements, and an inverse map from G to G that tells me what the inverse of an element is. And there's going to be some compatibility conditions that I'm not going to care about. Like you can write associativity in such a fashion and so on. That's what a group is. Right? Now, to get a Lie group, I'm going to ask for this group to be a manifold instead of a set. Okay? I'm going to ask for these two maps, multiplication and inverse, to be smooth maps, and what you end up with is a Lie group. Okay? So, what is a manifold? A manifold is something that locally looks like Rn or Cn if you are doing complex manifolds. Okay? Why do you consider manifolds? You consider manifolds because you can locally do calculus. Calculus is a very, very local subject. So, if you want to do calculus on some, if you want to try and do calculus on some surface like this, it's fine, because if I want to understand the derivative or something at this point, then I just look at some small neighborhood, and that looks like a small neighborhood of Rn. So no problem, you can do your calculus. Okay? What does it mean for a map to be smooth? It just means that it's infinitely differentiable, for example. The reason I'm trying to tell you this is that you could replace this with any other thing. You could replace manifold with a variety and these to be polynomial maps. You could replace it to be a topological space with topological maps, and you get a topological group, and so on. Okay. So what are the examples of Lie groups? It's the same ones that I've told you last time. You have basically these classical groups like GLN, SLN, special orthogonal group, finite groups. And if you're wondering how finite groups are manifolds, they're zero-dimensional manifolds. And multiplication map and inverse map are smooth for no good reason at all. Okay. Torus, the complex numbers with addition the real numbers with addition, if you like. The unitary group, the set of matrices such that A times A conjugate transpose is identity. S1 cross S1. S1 is, by S1 I refer to the circle. Yeah, you can take S1 cross S1, which you must have seen the picture at some point in your lives. Is a donut. Yeah. So these are all manifolds. You can do calculus on these things because locally they look like R2, for example. Okay.
Like discrete, like infinite group, like
Z would not be a Lie group. No. Well, I mean, it's a technicality whether you want to call it a manifold or not. Please do stop me if you don't understand something. It's not, nothing I'm saying should be all that hard, just maybe not very familiar. Okay. Okay, so let's say I have a Lie group, which I draw like this. This is my Lie group. Inside here, there's a special element called the identity. Right? Now, if I want to go to some other element, which I'm going to call G, then I have this multiplication map by G that sends that, that's a map from the group to the group, and it will send any element to G times that element. In particular, it sends the element E to G. Okay. Now, when I draw this, what I mean is the tangent space to identity for this manifold. Okay. So, again, you can just go back to calculus, right? If you have something that locally looks like Rn, your tangent vectors can be in all n directions. That's the tangent space. So, if you make such a local identification, then the tangent space is just Rn. It's basically all the tangent directions that you can have. Okay, that's a vector space. It doesn't live on this manifold. Okay. Now, you can look at G, and you can also have a tangent space. All the directions that you can go while still staying within the group infinitesimally. Okay. And what this multiplication map will do is, okay, so this I will denote by tangent space at identity to the group. This I will denote by tangent space as little g to the group. So this multiplication map will identify for me the tangent space at identity with the tangent space at G. Okay. So if you have a tangent vector at the identity and you push it forward with this map, you will get a tangent vector there. Okay. And why will it be an isomorphism? Because you can go back by multiplying with G inverse, for example. Okay. So what is nice about this group is, okay, it is a manifold, but somehow you're able to identify tangent spaces at every point with the tangent space at identity. Okay. So this is a feature that is usually used under the the word that usually represents this feature is homogeneous. It looks the same all over. Okay. Now I want to define the Lie algebra of G, which I am going to denote by this fractal letter, just because I can't keep writing Lie of G all the time. Okay. Also because I will end up using it anyway when I don't think about it. Okay. So this guy is the space of all left invariant vector fields. So let's get this slowly. What is a vector field? Okay. A vector field is the assignment of a tangent vector to each point. Okay. This is something you've seen before. I teach my calculus students this. This is a differential equation. Okay, it's a differential equation if you do it on Rn or something. Anyway, okay. So a vector field is at every point you give me a tangent vector, right? Asking for it to be left invariant means that under this identification, the tangent vector you gave me here should go to the tangent vector you gave me there. Is that okay?
I got confused.
Cool.
At every point you assign a vector space or a single?
No, a single vector.
Okay.
Yeah. So a vector field is the assignment of a single vector to every point in the manifold. And left invariant means that because we identify the tangent spaces, whatever vector you picked here should be the same vector that you picked here under this identification. Right? In particular, it means that the vector field is defined by whatever the tangent vector you picked at the identity. That holds all the information, right? So you could also think of this as just the tangent space of the identity. But this is only as a vector space. It has more operations on it. Okay. So let me just define for you formally what this Lie algebra is. So a Lie algebra G is a vector space with a bilinear map that I will denote by commutator. Let me write it this way. X comma y goes to x, y, no. Okay, such that one, it's q commutative, this bracket, and the second one, there's an identity that I like to write in many ways. The only problem is, I could have told you that the Lie algebra was just the tangent space of the identity. Yeah? If I told you this, you would never understand where this map is coming from. Okay? Where this map is coming from is that there's a commutator product on vector fields that's well known in differential geometry. And basically the point is that it doesn't mean anything to multiply vector fields. But it means something to take the commutator of vector fields. And that's what gives you such an operation. And this operation satisfies a certain identity. Okay? Neither of these will be very crucial to us. But what is the point of the Lie algebra? The point of the Lie algebra is this. You want to study this Lie group. Okay? And you said you can go from the identity to any other point by these multiplication maps. Right? And so what you want to do is, if you look at the tangent space of the identity, it gives me a local picture of this group. And once you have a local picture of this group, you can then expand out and understand the rest of the group.
Did you define the operation?
I didn't define the operation. Yeah. Yeah, I won't define the operation. It won't be so necessary for us what the operation is. But I will give you examples. Okay, so let me just see that I'm not missing out on something. Okay, so here are the examples of all those groups that I told you. So if my Lie group is GLN, then my Lie algebra, which I write with this fractal letter, is just n by n matrices. Okay. Now here's a sanity check. what is the dimension of this guy? The dimension of this guy is n squared. The dimension of the tangent space should also be n squared. And then what is this bracket operation that I wrote? In this case, it's just x times y minus y times x. Okay? And here is something for you to maybe know or check at some point, is that with that formula, this identity holds. Yeah? And then I give you some more examples. Suppose I take SLN, matrices with determinant 1. Then its Lie algebra will be trace 0 matrices inside n by n matrices. Okay? And the reason I give these examples and not just stop at GLN is because if you just see GLN, you have this, people tend to get this notion that the Lie group is basically all the invertible elements of the Lie algebra. That's not what's happening. Okay? So this GLN and this this n by n matrices, they're playing they're not sitting inside the same thing. They're playing slightly different roles, and you start seeing it when you look at subgroups.
Can you say why these can be viewed as tangents of those? Or?
Okay, so GLN, this is all invertible matrices. This is sitting inside n by n matrices. In particular, if you look at the identity matrix, which is this, and you look for what the tangent space is, it's going to be all of n by n matrices. So the thing that you need, that maybe I just write down here very quickly, is that if I have a vector space, right, then I can identify the tangent vectors at any point with the vector space itself. Okay? And the reason you're able to do this is exactly why you don't learn about tangent spaces when you first learn calculus. Because you're always inside Rn, you've always identified the tangent vector with something inside Rn again. Okay? And so the point here is that GLN is a subset of a vector space, which in this case is just n by n matrices. And it's a full dimensional subset. It's got dimension n squared. Okay? And therefore, if I look at the tangent space here, this is just going to be the tangent space of the identity for whatever this vector space is, which just happens to be the vector space itself. You're able to identify it. Okay?
Would you also say there were derivatives of that?
Yeah. Right. Okay. Then you have a slightly more complicated example. Suppose you took the orthogonal group, which looks like x times x transposes identity. Then the Lie algebra is x plus x transposes identity, which is Q-symmetric matrices. Okay. So I want you to notice that this becomes that, is a sort of linearization of whatever condition you had here. We'll see that a little bit more sometime. And then you have the torus, which is C star to the n, and its Lie algebra is just going to be C to the n, and this bracket is 0. It's a commutative Lie algebra, they say. Okay. Now I'm going to tell you one more feature of this Lie algebra, and one that tells you why it's good to understand the Lie algebra. Why you can understand a lot of the Lie group with just the Lie algebra. So what did I want to say? Okay. So this is what's called the exponential map. So the exponential map, it's a map from the Lie algebra back into the group. Okay. So in these cases, let me tell you exactly what it is before I tell you what it is. So in the case of GLN and all its subgroups, exponential map is just exponential. Yes, whatever is in the Lie algebra is a matrix, and you just do identity plus x squared over 2 factorial plus so on. Okay, that's exactly what it is. And if you come down to this torus, where this bracket is 0, then so something in the Lie algebra is just n numbers. Yeah, and the exponential map will just take the exponential of each of those numbers. Is that okay? Cool. So let me tell you what this exponential map is. So this exponential map does the following. You have this tangent space at the identity, right? So let me get this picture right. I'll always mess it up. So you have the identity, and let's say I take something in the Lie algebra. It's a vector field, but it's also determined by what vector I gave at the identity. Yeah? So this was my tangent space. I gave the vector x. I go to some other point, whatever x is, and so on. So I have a bunch of vectors that do this. Right? Now, an integral curve is a curve that follows this vector field. Okay? So you find a curve that follows this vector field. So this is the vector field x. This is an integral curve. Okay? If you think of the vector field as a differential equation, that's a solution to the differential equation. Okay? And so let me call this integral curve, what do I want to call it? Psi of t, t for time, psi x of t. So then what you're going to do is, you're going to take this integral curve that just follows the vector field, and you're going to see where it is at time 1. So where is it at time 1? So this particular one, you go time 1, that is psi x of 1. That's the exponential. What's the key feature? The key feature is that, so this is my Lie algebra, which I can think of as the tangent space, and this is my Lie group, and it takes a small neighborhood here to a small neighborhood of the identity, and this is a diffeomorphism.
What did you draw here?
So I have this exponential map. So this exponential map is from the Lie algebra to the group. I drew a picture of the Lie algebra. I drew a picture of the group. And I'm saying you take a small neighborhood around 0, which is an element of this tangent space, small neighborhood, and you see where it goes. And I claim it's going to go to some small subset around the identity in the group. Okay? And I'm saying that this map is a diffeomorphism. So it's smooth, and the inverse is also smooth. Okay? What has this allowed me to do? This has allowed me to take some small neighborhood of this Lie group and make it some subset of the linear space. Right? And the point is, this is a group, right? So if I can understand the small neighborhood of the group, then you just multiply elements within the group and you can propagate to the rest of the Lie group. Okay? If I multiply 2 elements which are inside the small neighborhood, I will end up with something outside. And you multiply, you will propagate to get the whole group. Okay? So what I'm going to say is that this neighborhood generates the group. What's one way to understand groups? By the generators. Yeah? You have something like a Lie group, you don't expect a finite list of generators. That's just way too much to ask for, right? Yeah? And if you don't have a finite list of generators, you want some way to understand what these generators are. And you are in this setting of differential geometry or calculus. So what do you ask for? You ask for some nice subset in this setup, and a nice subset in this setup is a neighborhood, right, that happens to generate your group. And it so happens that such a nice subset is parametrized by a vector space. That's about the best you could ask for, right? You've pulled the story back all the way to vector spaces. Okay. Now, yeah.
This integral curve t, what is this parameter?
Okay. So here's what it is, right? So this element of this Lie algebra is a vector field. So a vector field means I have a tangent vector at each point. An integral curve means, start at time 0 here and follow the vector field.
Okay.
Yeah. So it's telling you at this point go in this direction with this speed.
It's probably worthwhile to say that if your manifold was Rn, then these integral curves would be straight lines. I mean, the vector fields would all
Right.
point in the same direction,
And then
this
you just follow.
integral curve would be a straight line. And more generally, straight lines are geodesics in Euclidean space. And it is general about any manifold that the exponential curve and the integral, the exponential map and the integral curve will give you geodesics in that manifold. That's beyond, we don't need metric
Right.
stuff here, but this is a property of the exponential map. It's this unique map that gives you, it's another way to get it or to characterize it. It generates the geodesics of this.
My only question here is you want, I guess, one curve per vector basically, right? So then here I only see one curve, sure, because there is just one vector at the identity, and then you get just one integral curve. But
Right.
you want
A different field, you get a different.
So if I change the x,
One thing, just one vector. Yeah, okay.
yeah. Okay. And now let me tell you just a little bit about how to go back. So basically the key point here is that you can go back. And the key point is that if you take the derivative of exponential of t times x at t equal to 0, you will recover x. This is about as natural as you can think of if I told you those formulae. Okay. So let me tell you what.
How do you think about this? You say it's a key point. But what is the data that you get that you do the derivative to?
Okay, so what do I think about this? All I'm saying is these things you think of as elements of the group. They are elements of the group, but in a particular fashion. And you're taking the derivative and you're getting back something in the Lie algebra. So the exponential map is a way to go from the Lie algebra to the group. And this is the way to go back.
Okay.
So if you want to make an argument on the Lie algebra side and move forward, you use that. If you want to make an argument on the Lie group side and move back, you use this.
Okay.
Yeah. Okay. So let me hold on. Excellent. And finally, what I want to say is, let me see where is this. I want to talk about this. What's called the subgroups subalgebra correspondence. Okay, here's the correspondence. So suppose you have some Lie group, and its Lie algebra is then I want to say connected Lie subgroups of this Lie group that I have are in bijection with Lie subalgebras of this guy. Okay, so the 2 points to it, right? First is it's a one-to-one correspondence, which is telling me that if I have a Lie group and I want to understand what its subgroups are, it's enough to understand the subalgebras of the Lie algebra. Okay? this is another one of those things that I started with, is if you want to understand the subgroups of a group, that's not a linear problem. Right? That's not a linear problem. If I want to understand the subalgebras of something, that's a far more linear problem. I just have to determine certain subspaces that happen to be subalgebras. Right? Now there's one thing I added on this side. I added the word connected. Okay? And this should not surprise you, right? Like if this Lie group was just one component, somehow this tangent space at the identity will capture everything about this component. But if it had other components, you don't get there, right? This exponential map will not get you there. It will not let you leave the component. Yeah? So that's why I need connected. Okay. So the point here is that so if you go back to what we were looking for, we were looking to compute some subgroup of GLV, right? And so if whatever this subgroup is, you can understand it by understanding what the subalgebra, corresponding Lie subalgebra is. Okay, up to this finite group, at least the connected component of identity. Right. So the point is, you can determine GS by determining its Lie algebra. Because this is a subgroup of GLV by determining its Lie algebra as a subalgebra of GLV.
As a subgroup was determined by the action of G on a particular ideal, you need the corresponding action.
I need the corresponding action. Yeah. So let me just say one thing, and then we'll take a break before we get into some computations. So let me just write it down here very quickly. So if G is a Lie group and it's acting on some vector space, maybe I don't even need that. Okay. It's just acting on a vector space, and I want to understand, and let's say U is a subspace, and I want to understand all the linear transform, all the elements of this Lie group which preserve U. I claim this is the same thing. This is enough to understand the Lie algebra, which is a set of all elements in the Lie algebra such that it preserves U. Okay, I have to still tell you what the Lie algebra, how the Lie algebra acts, but let's hold off on that for a moment. But there are two things I want to point out here. First is that this equality here will necessarily become a subset. Okay, and the way to convince yourself of that, at least naively, is that groups have invertible elements. Yeah, Lie algebras will definitely not have invertible elements in there. So everything in the Lie algebra cannot possibly preserve U. Okay, there are some nilpotent elements in here, right? Yeah, so you shouldn't be able to always equal U when you apply something. You will lose some things. Okay, so that's one thing. The other thing I want to point out is, suppose you had some subset and you defined it to be all the elements of the Lie group that preserve the subset. It's simply not true that the Lie algebra will preserve the subset. Even if you put, explicitly contained and or equal to something. This is just simply not true. Okay, and the way to see this is precisely the fact that Here's exactly what's happening. When you're looking at it as a subspace, you can fudge the tangent space on the subspace itself. When you're looking at a subset, tangent spaces cannot be fudged into a subset. Tangent spaces are always a vector space.
Say it again?
So here I'm considering a subspace, right? So if I want to understand what's happening, so I have this W here, and I have this subspace U here. If it's a subspace and I look at the origin here, I understand the directions that determine the subspace. But if I have some subset, I understand the directions, that's not a subspace. Yeah? Not a subspace. But also this subset doesn't have to be sort of like another thing that, okay, so maybe what I really wanted to say was, if you know that it's a subspace, if you know that U is a subspace and you understood what the neighborhood around the identity is, you know what the subspace is. If it's just some subset, what's happening at the origin does not tell me about everything else. Okay, so this is just completely wrong. This is much better for us. And this was also the reason why I switched from a subset to something that's linear. So let's take a break and then we'll put it all together to see where we can do computations. Okay, so let me remind you what we were trying to do.
Managed to write new things on the board.
All the time, yeah. No, just that one thing. That's going to stay forever. Okay. So let me remind you what you want to do. There's a very particular subset of a particular vector space whose group of symmetries I wanted to compute. Right? It's a set of all linear transformations that preserve this subset. And what did I do? I decided to, instead of looking at whether it preserves a subset, to whether it preserves an ideal or parts of the ideal. Right? And then what did I do? Using this, I said, let's make this a Lie algebra computation. Right? We said to determine this group, I will determine its Lie algebra. So if I'm going to do the Lie algebra, I have to tell you how the Lie algebra acts. Okay? Which I won't derive for you the formula, I will simply tell you what the formula is. So if I take something in, okay, so V is a vector space, n dimensional. So then GLV is n by n matrices. I want to know how something in GLV. Sorry? No, this is the Lie algebra.
Oh, that's already the, oh, this G is actually the.
This is the Lie algebra of GLV. Yeah, sorry. So if I take something in this, and I take some function, which is a polynomial function in my vector space, I have to tell you how it acts. So this is an n by n matrix. So this looks like M11 all the way up to MNN. Okay, maybe M was the bad choice here. Maybe I take P. P1N. This guy, how does it act on F? It acts by sum of Pij xi del j acting on F.
What is the general thing you're showing us an example of? Or what?
Okay, hold on. Let me just write down something and I'll tell you. Okay, so what I said was, I said that if I want to understand the group of symmetries, I have to understand what it is. Instead of trying to preserve the subset, I'm trying to preserve the ideal or some parts of the ideal.
Oh, okay, so this
Right?
C of V is our.
C of V is the polynomial functions. The ideal is living inside the polynomial functions. So I want to understand the action on this polynomial functions.
So, for elementary people like me, so C of V, I can think of it as polynomials in n squared variables.
N variables.
N variables? V is n
Polynomials in n variables, yeah.
Even simpler.
Yeah.
Okay.
It's polynomials in n variables, and I want to tell you how a matrix, which is what a Lie algebra of GLV is, yeah, how does it act? It acts by a derivation, and here I just write del j to say d over dxj. Okay, so one feature about this is that it preserves degree. Okay, and another feature about it is if f for a monomial, okay, I'll get to it when I get to it. Let's just leave it there. Is that?
The derivative of j.
Yeah, it's the jth derivative. Okay, that's how it acts.
It's not clear that it's an action, but it's.
Well, yeah. Yeah, I won't derive the action for you. You just have to believe me that this is how it acts. Okay. Now, what's going to be the trouble in our case? In our case, this vector space is going to be m tuples of n by n matrices, which means it's not naturally indexed by 1 to n. It's not even naturally indexed by 1 to mn squared. It's naturally indexed by ijk. So that's going to make my formula look a little bit more messy.
Oh,
Okay, but just watch out for that. I mean, that's why I left the formula up there, because in general it's going to look a little bit more messy, but we'll try to match it up as closely as we can. Okay, so we know how the Lie algebra acts. What else is left if you want to understand this this thing is I have to understand the ideal, right? That's really all that's left for this computation. I need to understand the ideal. So what does the ideal look like? Okay, so we had this vector space of m tuples of n by n matrices. Okay, so the vector space was n tuples of n by n matrices, and I had my subset inside that, which was all m tuples of matrices. I had written it a different way, but here's another way to look at it, is that the complex span of these matrices has no invertible matrix. That's the same thing as saying sum of ti xi is singular. Okay. Now the question is, I have to understand something about this ideal to make this computation go forward. Correct? I'm going to make some claims about the ideal.
Before this,
Yeah.
we have this for all T1, etc. Tn.
Right. Yeah.
This kind of singular spaces appear in lots of places in mathematics. Sort of, it's very complexity theories think that we made up PIT. This is PIT, and people in algebraic geometry and in combinatorics actually, and in many areas just care about singular spaces. Just give you a set of matrices. If you look at the span, like written there over C over any field, do we get only singular spaces, singular matrices? It somehow is it's a basic problem and a difficult one.
Yeah, it's difficult.
Yeah, maybe this explains somewhat why it's difficult to know. Basically.
Okay, so I walked you through a lot of computation steps. At each step, I tried to make it into a linear computation. I succeeded in making it a linear computation, modulo the fact that I have to understand something about the ideal. Right? So I have to understand what the ideal of polynomials in mn squared variables that take 0 on this whole subset. Okay? I'm going to make a few claims, which I will try to come back to if I can and tell you how it works. And the first claim, okay, so first of all, this subset is closed under scaling. If I just scale all of these by a single number, it's going to be in the subset, which means that the ideal will be homogeneous. Okay? And I'm telling you that the degree d part is going to be 0 if d is less than n. and it's the same n. Okay? This is an exercise. Everybody should be able to prove this if you think for just a little bit.
You have to say what it means if the ideal is homogeneous for people to understand.
Okay, an ideal is homogeneous if it's a direct sum of its graded components. Yeah? Okay. Okay, here's what I'm saying. Here's concretely what I'm saying. If you take a polynomial of degree at less than n, there will be some point in the subset that it doesn't vanish on.
Is it here maybe even homogeneous with respect to some multi-grading?
It is.
I see. So where you look at each matrix individually,
Yeah.
values of each matrix
That's right.
individually.
Yeah. It is, but I won't go that far here. I do use that later on, but I won't go that far here. Okay. Okay, and now let's think about any. Okay, can you think of any polynomial that vanishes on this? The determinant of the first matrix, the determinant of the second matrix, the determinant of any linear combination of the matrices. That's kind of how this is defined. Okay, so if I take all such determinants of linear combinations and I look at their span, these are all degree n polynomials, right? These are all degree n polynomials that vanish on this subset. And I claim that any degree n polynomial that vanishes on this subset must be a linear combination of such things. This is a non-trivial claim. Okay, so I want to say this is easy, and I want to say this is hard. Okay, but I guess one thing that I want you to notice is that if I look at the zero locus of these polynomials, I recover S, which was needed for my computation.
You can say hard, it just uses representation theory.
It uses combinatorial representation theory, which I might hint at the end. I might at least hint at how you might do something. I mean, you should think. You just think about this, right? Somebody gives you a subset of a vector space or something, and asks you, can compute all the functions that vanish on it. How do you do this computation? How do you do such a computation, right? You need some tools. You need some help from somewhere. And I'm going to use representation theory to get this, but I will not get there now. I will use this and continue and come back. Okay. So the theorem that we prove is basically we compute the group of symmetries using this technique that I've broadly stroked out for you. And and here's exactly what the group of symmetries is. There's a GLN cross GLN cross GLM. This is left multiplication, this is right multiplication that we've all seen before. This GLM is a particular action that basically looks like, takes this tuple, thinks of it as a vector, and does matrix vector multiplication.
Another way to say it is that it's a change of linear change of variables of the T of the linear combination. Like you have the sum Ti xi, and there are m variables Ti. So you just change linearly the variables Ti. It shouldn't change the span.
Yeah, that's clear? Cool. And then the Z mod 2 is transpose. If you take every matrix in there and transpose it, it won't change whether the linear combination is an invertible matrix or not. Okay? It's easy to see that all of this is inside the group of symmetries. It's almost always easy to see that certain things will preserve a subset. The hard part is to show that nothing else will. Okay, and to do that, I will do the Lie algebra computation. Okay, so let me make things easy for us, right? So I won't do this entire computation. I will do it in the case when m is equal to 1. Okay, and if I take m is equal to 1, the subset becomes much nicer, something that you might have studied for so many reasons. Okay, the subset just becomes, okay, first of all, the vector space becomes just one n by n matrices, right? I've taken out m. It's just n by n matrices. And I look at the subset of singular matrices. Is that clear? It's just a subset of singular matrices. And the claim is the group of symmetries is GLN cross GLN semi-direct product Z mod 2. And the GLN cross GLN is left and right multiplication, and the Z mod 2 is transpose. This is something you learn in linear algebra right in the beginning. Determinant equal to 0 or not equal to 0 is preserved by multiplying on the left by an invertible matrix, multiplying on the right by an invertible matrix, and taking transpose. Okay? Now the fact that there is nothing more was proved by Frobenius back sometime in the 1800s. There's another proof of it by Dieudonné. I don't know if that's how you say it. I'm not. Dieudonné. And you see a few proofs floating around in literature, and they all use different things. One of them uses the fundamental theorem of projective geometry and so on. And I guess the smartest proof uses the fact that there is no subgroup between this and GLV. So there is no such subgroup between the two of them, algebraic. Okay, but anyway, so there are a bunch of proofs of this, but I want to give you a proof using all the ideas that I just gave out, which for some reason nobody's done before.
Well, this is the only one we know that generalizes to M tuples.
Yes.
Is there going to be a continuation for this theorem, talking about the null cone? Or?
There will be.
Okay.
I mean, first we have to tell you how to compute the symmetries, and then we'll get to the null cone. So let me give you a very quick idea of how you might do this computation, right? So the first thing is, in this case, it's much easier, but the ideal is just the determinant. It's just spanned by the determinant, generated by the determinant. Determinant equal to 0 is precisely the singular matrices. Any polynomial that vanishes on singular matrices must be a multiple of the determinant. It's much easier to prove. So this group of symmetries, which is going to be all invertible transformations that preserve my subset, will now happen to be all invertible transformations that preserve the determinant up to a scalar, sorry. And because it's up to a scalar, I can assume that the scalar is non-zero because these are group elements, they have inverses. I'm just going to wait. Do you understand what's going on here?
No.
Okay. So this is the ideal. The degree n part of this ideal is the C span of the determinant. It's one dimensional. And so what we said, and moreover, the zero locus of this is precisely the set. So preserving this set, this subset, is the same thing as preserving this guy. It's a one-dimensional space. What does it mean to preserve this guy? It means if you act it on the determinant, I must go back to the space. So it has to be some multiple of the determinant, and I claim the multiple has to be non-zero because it's a group element, right? So it has an inverse action. Okay. But then the Lie algebra would then be the set of all M in the Lie algebra, which now preserve the determinant, but because it's a Lie algebra, I won't ask for C to be non-zero. C could be 0 sometimes. Okay. Now let's think about it. This V here, in our case, is n by n matrices, right? So GLV is GL of n by n matrices, which is, this is basically matrices over an n squared. So it's n squared by n squared matrices. But it's not nice to index them by 1 to n squared. It's nicer to index them by I comma j. Okay. So if you take something in here, I will write it down in a block form. Okay, so this here is n squared by n squared matrices. Okay, I'm going to do this computation a little bit fast, so don't hold on the details. Just watch how the computation unfolds. Okay, so m1n, m12, mn1. And each of these mij's are again n by n matrices. Right? This should remind you of Kronecker products of matrices. Okay? Now, this mij so let's say I have M12, so I'm just going to pick the 1-2 guy. It's an n by n matrix, so let's just say it's going to be C11 to Cnn. Okay, there's a bunch of indexing that I'm not going to tell you exactly how it works, but let's do this. So how does this particular guy act by? Okay, so this thing acts by sum of Cij x 1I del 2j. Do you believe the indexing?
So the 1 and the 2 are the 1 and the 2.
Right. This one and this 2 correspond to these guys. Right? Remember, we're working inside n squared by n squared, right? So I don't want to index by n squared. I want to index by I comma j, where I and j are in n. Yeah. So I mean, it's variables over matrices. So variables are indexed by ij's. So that's why I have a 1i and a 2j.
The C's are the same for different blocks?
No, they won't be. They won't be. They'll be different for different blocks. Yeah. Okay. So I'm just trying to focus on one block so that you can see the computation. Now, the other thing I want you to notice is if you look at the determinant, sum over minus 1 to the sigma x1 sigma 1 x2 sigma 2 xn sigma n. I want to say this is multilinear. It's multilinear in the sense that it's degree 1 1 1 1 1, where I just look at the first of these guys. Okay, so if I set degree of xij to be ei, the ith coordinate vector inside z to the n, then I want to say the degree of the determinant, so maybe I call this multi-degree. Multi-degree of the determinant is, every monomial has this multi-degree. Is that clear? Now if you think about how something,
It's not quite true because there are n squared variables, so some of them are zeros and some of them are ones.
no,
So you look just at the monomial.
Yeah.
Each monomial is yeah.
yeah. I'm taking a multi-degree which is valued in Zn, not Zn squared.
How is it defined?
It's defined,
Well, the x1, if there was x1, 2 and x1, 3,
that would be degree 2 0 0 0. Yeah.
so you're summing a column.
Just the first, in this index, I only care about that. I don't care about this. Okay? So I have this multi-degree, it's 1 1 1. How does,
It's linear in columns, right? Of the matrix.
yeah, it's linear in columns. Okay? How does this particular expression act by? It takes out, okay, so what is this? It's going to take the degree from 1 1 1 1 1 to 2 comma 0 comma 1 1 1 1 1. Okay, you differentiate by a 2 comma j, that's going to reduce the second coordinate by from 1 to 0, and then you multiply by something that looks like a 1 comma I, that's going to increase that one. Right? Now look, and okay, so this was what M12 does, and no other Mij does this. Every other Mij will send you to a different multi-degree. Right? So whatever this M12 does, it takes this determinant and it gives me, in the output, it gives me a certain degree part of this output, and that degree part has to be 0. Because whatever this entire thing is, it must preserve the determinant, right? So the output should not have a degree 2 0 1 1 1 1 part. So this must act by 0. Yeah, does that make sense? Now if it must act by 0, then you just start searching for the coefficients of different monomials. let's say, for example, I want the coefficient of x11, x11, x33, xnn in M12 determinant.
Maybe just one high level point. I mean, there is this big Lie algebra, it's just n squared by n squared matrices. So the problem is linearized in the sense that we want linear conditions on this big space so that we pick up a subspace which will correspond to the group of symmetries that so the fact that it preserves determinant just gives us linear conditions on the entries of this big matrix. And hopefully eventually what comes out is a very simple looking subspace that will fit exactly with the group
Whatever.
we are looking for.
Yeah, and I'm just trying to give you a sample of the computation. Okay, and the sample of the computation is basically saying, okay, I restricted myself to a certain piece of this Lie algebra element, and it's doing something about multi-degrees that allows me to just look at what this piece does. It must act by 0. How does it act? It acts by this formula. And so if it acts by 0, I want to look at the coefficient of some monomial in the output. Yeah, so that monomial, for example, let's say is this guy. The coefficient should be 0. But how can I get this monomial? By applying one of these terms to one of these guys. Okay, so now if you think about it, the only way I can get this is that these terms should be x33, x44, x55 all the way up to xnn. Right? Nothing's happening to them. That's the monomial. So in the first, so that means the first two terms must either be x11, x22 or x12, x21. Right? If it was x12, x21, you could not get rid of the x12 because you can only get rid of the 2j part of it. So that monomial cannot contribute to this in the end. So the only way you could have done was you started with x11, x22 all the way up to xnn, and then you performed 2 to 1, 1. Okay? So the coefficient is just going to be C12. But this must be 0. Yeah, so you get some really nice conditions like this, and it's not so hard to prove this. And so what you end up with is, okay, so let me just hold on here. You end up with the fact that M must be of the form A tensor identity plus identity tensor B, which is exactly what the Lie algebra of GLN cross GLN would look like. Yeah, I can tell you why in just a minute. Okay, so let me tell you why that's how the Lie algebra should look like.
To get this form of M, you just what you pick up, just like in this example, you see that many of the entries must be 0, and some other entries must be equal to each other, and
that's all you need to get that. Okay, so
in M1, 1, 2, all the diagonal elements must be 0.
all the exactly right. So you use symmetries to make these kind of arguments. In M12, I have to show that all the off diagonal entries must be 0. But if you realize it's the same argument with just a different looking monomial here. Yeah. So I've already gotten a piece of that.
So, did we find out that G sub S is this?
Yes, this is my claim. That, which is just you repeat these kind of arguments over and over again, and you end up with that.
Okay. And your statement there is saying to us that the capital G sub S is that?
Yes, almost. But
Almost?
there's a transpose, right? The connected part of capital G sub S is that.
Oh, okay. It's disconnected, this transpose.
Yeah.
Sure.
And so, okay, but I'm just trying to tell you why you should expect this to be the Lie algebra. Basically, the group acts like this, right? GL of. So I have the left and right multiplication. How does this go? This goes P comma Q, and if you write it down in terms of like indices, it's this Kronecker product of matrices. Yeah, that's a bilinear thing. What do you think happens when you differentiate a bilinear thing? You get something that looks like that. Yeah? Okay, so let me leave it at that because it's too much computation otherwise. Okay. No. It's a okay. I can't read Frobenius's paper. It's in a language I don't understand. But I asked somebody else, and it doesn't seem to be what Frobenius has done.
I guess the point is that form is like it's the product rule.
Yep, exactly. That's what it is. Okay. So let me summarize what I've done, right? What I did was I gave you a computation that told me how to compute the symmetries of singular matrices inside n by n matrices. Yeah? It was a computation that did what? It took the ideal, and I tried to figure out what are all the Lie algebra elements that fix the ideal. And because the ideal was generated by this determinant that was so nice, had this multi-degree, I was able to break up the computation very nicely into just looking at different monomials and their coefficients. And I got a bunch of conditions that cut out precisely what I wanted. Okay? Do this on steroids, and you get that theorem. Okay? Now, when you look at this guy, there's one more degree you can consider, this multi-degree, and this is this M. And you use all of that, and you can get there.
Literally on steroids.
Actually, the extra part of the argument becomes not so much, actually. Okay.
I said, you know what to expect. You know what the answer should be. You hope you know what the answer should be. So it helps.
Right. Okay, so we don't have too much time. So let me give you again a little idea of how you use something like this to prove that. Okay, so I have to state the theorem, which I didn't state. So the second theorem is perhaps the main one. So if G is a reductive group, acting on m tuples of n by n matrices, then the null cone is not equal to the singular tuples of matrices. Okay? It doesn't matter what reductive group it is. The null cone simply cannot be the singular tuples of matrices. Okay? So I spent close to an hour and 45 minutes to give myself some kind of upper bound for this group. Originally, it should just be some reductive group. You can always think of it as a subgroup of GLV because it's going to act by linear transformations. You can think of it as a subgroup of GLV, which is GL of mn squared. Yeah, that was much larger, and I spent basically all the time up till now to remove that upper bound and give myself a better upper bound, which looks like GLN cross GLN cross GLM. Okay, I'm going to ignore the Z mod 2. It doesn't really matter because if I'm trying to look for whether 0 is in the closure of an orbit or something, a finite group isn't going to help me. Okay, so I forget the finite group. It's not going to be the issue. So now I have to look at subgroups of this. Yeah, but it's still not that easy because these things have lots and lots of subgroups. You can't just sit around and rule out every subgroup at once. Every subgroup one by one, or even classes of subgroups. It can be pretty complicated. So I don't know what I have in mind. Okay, so let me remind you of some of the things that we did last time. So this is null cones for torus actions and this Hilbert-Mumford criterion. maybe I just put it as Hilbert norm. Okay, so let me remind you, if I have a group acting on a vector space, the null cone is a set of all vectors such that 0 is in the orbit closure. That's a capital V. Now suppose I had a torus acting on my vector space. Okay, so here's one thing that I said last time, and hopefully some of you remember it, and if you don't, this is the first time you're hearing it, is you have a basis of your vector space for which the action of every element in my torus is diagonal. Right? So if these are going to be eigenvectors for every element in my torus, then they have a corresponding eigenvalue, and that eigenvalue is a function. It's a function from my torus to complex numbers. Yeah? And we said these things can be identified with z to the n. They have to have a special form. And then what did I say? I said, take something in here, right? Now, V is in the null cone if and only if the convex hull of lambda I, where I is in the support of V, doesn't contain 0. Okay? So I said this last time, but let me slowly repeat it. You want to see whether a particular vector in here is in the null cone or not. Okay? You look at its support. Its support is some subset of 1 to m. You take the corresponding weights. These are called weights. These weights are some vectors inside z to the n. You look at the convex hull of those weights, and you see whether 0 is in it or not. Okay? You don't have to worry about why this is true or something. This is this linear programming thing that I tried to tell you last time. I proved it last time. Yeah, but I see some new faces. So, okay, I shouldn't put G here. Let me put Tn. Okay. So what this means is that the null cone for a torus, the capital V, sorry. So the null cone for the torus action is a union of what I call coordinate subspaces. Is this a term that makes sense? It's basically saying certain supports are good, certain supports aren't good. If your support is contained in some particular subset, then you will be in the null cone. If your support is not, then you're not in the null cone. Yeah? So it's going to look like the xy plane plus the yz plane, things like this, maybe 7 dimensions of different kinds of coordinates. Okay. Now there's one more theorem that I'm going to state, which also I stated last time, which is due to Hilbert and Mumford. And this is that, okay, suppose you have some group acting on a vector space, and T is a maximal torus of this group, which just means the largest subgroup which is isomorphic to a torus. Okay. Then if you want to understand the null cone for the group action, it's enough to understand the null cone for the torus action and move it around by the group. Okay. So between this and this, you have some understanding of the null cones. Okay? Now there's a very small trick here. Okay. Now, whatever hypothetical group that could have been whose null cone was the singular tuples of matrices, we know as a subgroup of GLN cross GLN cross GLM. Okay? We're searching for such subgroups. what is the maximal torus here? The maximal torus here is Tn plus Tn plus Tm, where Tn is just diagonal matrices. Diagonal invertible matrices is C star to the n. Yeah? Now, that's the maximal torus here. This group will also have a maximal torus. And my claim is there's a little trick that people in Lie algebras know very well, is that all maximal tori are conjugate. And what this allows you to do is it allows you to say without loss of generality that your maximal torus is inside that.
This G is our G sub S?
This is not G sub S.
A subgroup of G.
This is what, yeah, this is the hypothetical. This is the hypothetical group for which the null cone could have been what I wanted. Okay, so then I know the maximal torus is a subset of this. Why I'm happy about this is that this particular maximal torus, right? All the xi, jk, each entry of these m tuple of matrices is an eigenvector for anything in here. Yeah? That means it remains an eigenvector for anything in here. Right? So when I'm trying to look at the action of this on m tuples of n by n matrices, the standard basis is already an eigenbasis, which means I just have to look at the weights for the standard basis and so on, which means that the null cone is going to be a union of coordinate subspaces in the standard basis that you know. Okay? So this means that the null cone for the torus acting on is going to be a union of coordinate subspaces in the standard basis, but I won't write it. Okay? Then there's something that you can prove. You can prove that any coordinate subspace in singular tuples of matrices is the same thing as a coordinate subspace in this non-commutative singular tuples of matrices. This is just a structural feature that I know because I've been working with these things for years.
Say again? Sorry.
So, if you took a coordinate subspace inside singular tuples of matrices, it also happens to be a coordinate subspace inside non-commutative singular tuples of matrices, which maybe you've forgotten, but this was the non-commutative analog of singular tuples of matrices. It was all, maybe let me write it down here. Well, okay, maybe you don't care that much. It's the null cone for the left-right action. Okay? So, both of these have the same coordinate subspaces, which means whatever this null cone for this torus action is, it has to live inside here. Okay? So, the null cone for the torus action is sitting inside the non-commutative singular tuples of matrices. Okay? Now, the null cone for whatever the group is has to be G times the null cone for the torus, which is going to sit in, which is going to sit inside what? G, I'm going to upper bound G by this. Is that okay? So let me just call this G sub S, because that's what it was. So I'm going to upper bound G by G sub S. I'm going to upper bound this null cone by this guy. It's not hard to see that the null cone for the left-right action is also stable under the action of GLN cross GLN cross GLN. Okay? Which means this is a subset. Well, okay, not just a subset, now it's equal to right? But what do we want? We want the null cone to be singular tuples of matrices. Yeah? So as long as this guy and that guy are different, you can't have it.
You want it to not be contained.
Yeah, but this is bigger.
Yeah, this is, yes.
Singular commutative
So this is an assumption that I forgot to state, is I need something very mild. I need at least one of these numbers to be greater than 3. Otherwise, those two things are equal. And so let me show you why they're not equal. And I will show this to you by an example.
You wrote the chain of containment. So
Yes.
how is this a counter?
The contradiction is that I will show this. I will show this for n greater than or equal to 3 or m greater than or equal to 3. This plus that is a contradiction. Okay, and the way to show it is this is very everybody who's worked on anything close to here knows this example.
Visu, before you give the example which proves that it's contained but not equal to, I think that everybody should see that it's at least containment, right?
Right.
Yeah.
Here's one way why it's containment, right? On one, I took linear combinations and I asked whether it was singular over the free skew field or whether it was singular over the function field. If something is singular over the free skew field, it's definitely singular over the function field, but not the other way around. Okay? And here's an example that people just seem to know. This is inside singular tuples for 3, 3, but it's not inside non-commutative singular tuples. Okay, so for one thing is easy. It's easy to see that this is inside singular tuples. Any linear combination of these three is a skew-symmetric 3 by 3 matrix. That's always singular. Okay, but if you take this guy, T1, T2, T3, 0, 0, 0, minus T1, minus T2, minus T3, and you do Gaussian elimination to try and understand the rank. Yeah, Gaussian elimination is valid even over free skew fields. You just have to know it. And if you do Gaussian elimination, you will end up with something that looks like this. And this is an expression that Jeroen probably recognizes. You will get an expression like this, which if you thought of the TIs as non-commuting, this is a non-zero expression. And therefore, this is not inside non-commuting singularity. Okay? So it's you have to really work. You have to really work a lot to get here. At the end of the day, it's still a negative result, but okay. There's one part that I didn't tell you about. I didn't tell you how to capture the ideal, but maybe I won't tell you how to capture the ideal because I'm tired more than anybody else.